Stop the line! Hold production! An EV charging company had just finished assembling 12,000 PCBAs. Everything looked fine until the final burn-in test. At minute 37, the first board failed. Within 1 hour, 217 test boards were destroyed. The engineering team spent 3 days and nights checking everything. The MOSFETs were original parts. The resistors and capacitors were within tolerance. The soldering quality looked good. The schematic was reviewed again and again. No obvious mistake. Then, a senior engineer with 20 years of experience walked in. He picked up an infrared thermal camera, looked at an unpowered board for about 10 minutes, pointed at one tiny via on the PCB and said, "That's the problem." The room went silent because the MOSFET was not the real root cause. The PCB was killing it. 1. The trap most engineers fall into: when a power MOSFET fails, what is your first reaction? Overcurrent? Use a bigger MOSFET. Too hot? Add a bigger heatsink. Bad component quality? Change to a more expensive imported part. That is the typical response. But in many real-world power device failure analyses, the root cause is often not the MOSFET itself. Common failure sources include thermal stress fatigue, parasitic oscillation, mechanical stress cracking. Only a smaller portion comes from true overcurrent, overvoltage, or bad silicon. In other words, a blown MOSFET does not always mean the MOSFET is the problem. Sometimes the PCB layout, thermal path, parasitic inductance, or mechanical structure is silently destroying the device. In this EV charger case, the issue was shockingly small. 1 via. The source pad of the power MOSFET had a via placed right in the center of the pad, and there was only one. During production, the copper thickness inside that via was slightly below the design target. When the board powered up, the current density around that via became extremely high. The temperature rose rapidly, and repeated thermal cycling caused the copper barrel inside the via to crack. Once the via resistance increased, it generated even more heat. More heat caused more cracking. More cracking caused more resistance. That is a positive feedback loop, and it ends in failure. Eventually, the via opened, the switching loop generated a large voltage spike, the MOSFET gate oxide was damaged, and the failure cascaded through the power stage. So the lesson is simple. A 30-cent via decision can destroy a $3 MOSFET. 2. The 4 hidden causes of power device failure. Let's break down the 4 most common hidden killers behind MOSFET and power stage failures. Killer number 1. Thermal stress. Thermal stress is not always dramatic. It does not always destroy the MOSFET on the first power-up. It behaves more like a slow disease. The board works during initial testing. It passes functional validation. It may even survive a short burn-in test. Then, after dozens or hundreds of thermal cycles, the solder joint cracks, the pad lifts, or the internal bond wire fails. I once saw a 500-watt DC-DC power supply that failed every time around the 7-2-hour mark during aging. The team changed MOSFETs again and again. Different brands, different current ratings, different voltage ratings. Nothing worked. Finally, we ran a temperature cycling test from -40°C to 125°C. After only 12 cycles, the MOSFET pad started separating from the PCB. Under the microscope, the solder layer looked like dry, cracked mud. The root causes were basic. Not enough thermal vias under the device. Vias were not properly filled or capped. The copper weight was too low for the current density. The thermal interface was inconsistent. The pad and copper area were not designed for repeated expansion and contraction. Thermal stress failure has a few typical signs. It does not fail immediately. The failure time is often repeatable. Damage appears near pad edges, leads, or solder joints. You may see solder cracking, pad lifting, or internal bond wire damage. The key point: if several boards fail after a similar operating time, do not only blame the MOSFET, check the thermal path. Killer number 2. Parasitic oscillation. This one is invisible on the schematic. On paper, your circuit may look perfect, but on a real PCB, every trace has inductance. Every copper area has capacitance. Every loop has impedance. At high switching speeds, these parasitic elements can resonate and create voltage spikes far beyond the normal supply voltage. Here is a simple example. A 10 centimeter power trace may have roughly 50 nanohenries of parasitic inductance. If the switching current changes at 500 amps per microsecond, the voltage spike is V1dt. That becomes about 25 volts. If the device is only rated for 18 volts in that part of the circuit, you have a problem. Even worse, the spike may last only a few tens of nanoseconds. A multimeter will never show it. A basic oscilloscope probe may also miss it, especially if the probing method is wrong. That is why a board can look perfect in the lab, but fail randomly in production. Parasitic behavior varies with layout, component placement, soldering, and manufacturing tolerances. This is why power loop layout is not cosmetic. It directly affects reliability. To reduce parasitic oscillation, keep the high current switching loop as short as possible. Place decoupling capacitors right next to the power device. Use a tight current return path. Add RC snubbers when needed. Adjust gate resistance carefully. Avoid long serpentine traces in power paths. A longer trace is not just copper, it is an inductor. Killer number 3. Mechanical stress. Power devices are physically large, thermally stressed, and often mounted with heatsinks or screws. That makes them very sensitive to mechanical stress. Common sources include lead-free soldering stress, V-score depanelization stress, heatsink screws tighten too much, board bending during assembly, vibration during shipping or operation. One real case involved a server power supply project. Boards started failing after several months in the field. At first, the team suspected thermal design and MOSFET quality, but failure analysis showed a different root cause. The mounting screws were over-tightened. The engineer wanted better thermal contact, so the screws were tightened beyond the torque limit specified in the datasheet. That excessive mechanical pressure created micro cracks inside the silicon die. The cracks slowly expanded during operation. Eventually, the device failed. This is why torque matters. A screw torque difference that looks tiny on the production line can decide whether a power module survives or fails. To reduce mechanical stress, use a torque wrench. Follow the datasheet torque limit. Avoid V-score lines near power devices. Use routed tabs or stress relief structures where needed. Reinforce the PCB in high vibration applications. Use packages and mounting methods suitable for vibration. Mechanical stress is often invisible until it becomes catastrophic. Killer number 4. Real overcurrent and overvoltage. Of course, sometimes the cause really is electrical overstress. The common cases are: overcurrent protection is too slow. There is no short circuit protection. The input voltage exceeds the device rating. The inductor saturates. The output is shorted. A surge event exceeds the protection design. These are real circuit design problems. But the mistake is assuming every MOSFET failure is caused by overcurrent or overvoltage. Before you replace the MOSFET with a bigger one, ask, did the layout create a local hotspot? Is the thermal path reliable? Is the power loop too long? Are there voltage spikes from parasitic inductance? Is the device under mechanical stress? Was the torque controlled? Was the board tested under temperature cycling and vibration? If you do not answer these questions, you may only be treating the symptom. What separates a senior engineer from the rest? It's not how much you know, it's design discipline. Here's an example. A junior engineer adds 4 to 6 thermal vias for a power device and calls it done. But a senior engineer, they lose 16 or more SI-SETO actual current and thermal requirements. Same with copper weight. Juniors run an ounce across the whole board, seniors spec 2 or even 3 ounces on power paths, and they verify current density. The real difference shows up in via placement. Juniors might drop a single via on a source or drain pad. Seniors deliberately avoid single-point current bottlenecks with multiple parallel vias. Juniors center thermal vias on pads without thinking about manufacturability. Seniors plan ahead for via filling, solder wicking, voiding, and thermal cycle reliability. Even thermal interface material. Juniors grab whatever grease is handy. Seniors specify controlled TIMs with proper compression ranges. So where's the gap? It's not about knowing, it's about executing properly. How do you prevent MOSFET board-level failures? Here are 8 practical rules. 1. Never rely on a single via for high current source or drain paths. Parallel vias are the right answer. 2. Don't place current carrying vias dead center on pads unless you've got filled and capped via in-pad process. Otherwise, solder sucks in and creates voids. 3. Control copper weight and current density. Power loops may need 2 to 3 ounce copper. 4. Keep switching loops as short as possible. Every extra millimeter is extra parasitic inductance. 5. Place local decoupling tight against power devices. Typical setup: small ceramic for high-frequency spikes, plus bulk capacitance for energy storage. 6. When you see high-frequency ringing, RC snubbers or gate resistor adjustments can help, but here's the trade-off: slowing the gate does suppress ringing, yet it increases switching losses. Always a compromise. 7. Control mechanical stress. Use torque wrenches during assembly. Keep V-scores away from power devices. For vibration-sensitive applications, pick packages and mounting structures that tolerate mechanical strain. 8. Design real protection. Fast overcurrent TVS surge protection, soft start, short circuit testing, overvoltage and undervoltage tests, full load and overload validation. None of these are optional. Before mass production, don't stop at room temperature functional tests. 3 tests are mandatory. Thermal cycling, think -40 to 125 Celsius adjusted to your product needs. High temperature full load burn-in running at maximum rated ambient. Mechanical vibration testing, absolutely non-negotiable for automotive, industrial, charging, and power conversion products. Remember, a board that only works on the bench won't survive in the field. Back to that charging station case from the opening, the fix was almost embarrassingly simple. Add 2 more vias to each MOSFET source pad, correct the local current path, problem solved. Later, the technical director said something worth remembering. He used to think power design meant picking a MOSFET, drawing a schematic, and bolting on a heatsink. Now he gets it. The real work is in the PCB. That's the heart of this video. 0.3mm vias, 1mm traces, 5 kg 4 cm screw torque. They look like minor details, but in power electronics, these small things determine whether your product survives mass production. Follow ICwantOpen for more real-world electronics manufacturing and failure analysis cases. From design to BOM, debugging to failure analysis to component issues, when in doubt, ask ICwantOpen.